Well, we're nearly there. Welcome back, everyone. This is sometimes the hardest part about class, just watching the seconds tick down until we get started. And it's official. Looks like we can begin. Welcome back. So we only really just started chapter 6 last class on Monday after finishing off chapter 5. And we did do the extra example of chapter 5, as well as finish off the original notes that were posted. Because of that, I felt like it was a good idea. Another student asked about this as well, to move the due date on quiz number 5 back by 1 week. That means this is kind of a weird week. We don't have any quiz due this one. Since quiz 5 from last time has been moved to this week, we get a bit of a breather, so it does not feel like it'd be the worst thing in the world. And we'll be going back into our weekly quiz pattern week by week after this one off here. So if you did quiz 5 early, then you can head it in early, or you can hang on to it until the official due date a week away from today. Aside from that, really the only thing other information to mention is we'll have our exam 2 on Monday, October 20. It's a ways away. It's going to be after midterm week. But on Friday morning of this week, I'm going to start working even before I grade. I guess I don't have quizzes to grade, but I'll start on Friday morning publishing the definite content of what the exam 2 will be about. I'm thinking it's pretty much going to be chapter 3 to chapter 6, but we'll put it down in writing. And I'll be posting all the review problem information that you would want to see as well as you study for that exam. It'll be the same exact write out as well for the allowable materials. So what it said on exam 1, it is closed book, but you're welcome to have a single page of notes, front and back, of size 8.5 by 11 inches. That's highly specific, but it's just a reminder, if you're using ordinary notebook paper, sometimes it's a lot shorter than paper of this size, ordinary letter paper. So I'm just mentioning that just to be specific. It can be a little bit bigger than some smaller notebook paper. And it's going to be heavily based off the TI-84 calculator, more so than exam 1. Exam 1, we just did some basis statistic computations. It was mostly a concept question. Exam 2 is going to have a lot of computations in, let's see, not as much chapter 4, but a basic calculator is helpful there for calculating interquartile range, maybe 1.5 rule of thumb. It's going to be more about chapter 5 using the normal model, section 5.4 problems, as well as a little bit in chapter 6, more about calculating the correlation coefficient. So that's what we'll be doing for pretty much the rest of this week, finishing off chapter 6, going into chapter 7. And I think the extent of exam 2 is going to be basically chapters 3 to 6. Since I don't think we'll have a chance to finish chapter 7 on this week, we'll probably be finished sometime on the next one. Well, any questions at all, folks, with the quick rundown of the announcements? Took 3 minutes this time. Okay, well, we left off looking into scatter plots. The big idea here is we're looking into 2 quantitative variables simultaneously and looking how they could be related. So first thing we want to get a handle on is just creating a scatter plot. Sometimes the best way to do that is just doing it by hand. That way we're just forced to see how everything goes together all at once. So this problem was about the phenomenon called environmental lapse rate. It's a pretty fancy name, but it's just the idea that the higher you go in altitude above sea level, the colder the average temperature tends to be. And just to see how strong the lapse rate is in the Teton range, in this made-up data, researchers collected altitude readings and the average temperature readings for, it's said here, average afternoon temperature. So these were kind of like the highs that they experienced in these altitudes. We mentioned that with this particular data, we do have 2 quantitative variables, but their roles are pretty specific this time. We're thinking that the altitude is going to explain how the average temperatures are varying in that particular pattern. So we're thinking of the response variable being temperature and the altitude being the explanatory variable for these particular data. Now, when we go to plot it, the actual explanatory variable is always going to be our horizontal axis, And the response variable will always plot as the vertical axis. In fact, that turns out to be really important in chapter 7. In chapter 7, the goal is to put a line through our data, the best fitting line. And if you interchange X and Y, you actually get a different line. Still will fit the points nicely, but the line is doing something different. Well, just to get a feel for this topic, let's start plotting these points. We carefully lay down the horizontal axis using the max and the minimum of the data for the X variable, similarly for the Y variable. And now it's just kind of like the warm-up problem that we did at the top of these notes. These are just pairs of numbers. It's kind of like doing a dot plot, but these numbers now have an altitude. So that kind of goes along with this topic. At 300 meters altitude, well, the height of it is 18.1 degrees. So we're at the kind of the maximum. We just put a 1 dot there. Then at 650 meters above sea level, we have a point at 16.2 degrees. This is Celsius. So 650, that's just going to be slightly to the right. My scale is kind of blunt since I went by 300 meters. So just eyeball it, put it the best spot you can based off the way you wrote your scale. And then keep on going down the line. 900 meters, average temperature was just below 15 degrees. So maybe about here. 1,250 meters. So this is getting close to about the altitude we are in. We're around 1,436 meters in Idaho Falls on average. So 12.5 degrees at this altitude. So 12.5 would be roughly here. And then just keep on going. 1,500 meters, temperature was 10.8 degrees. So right at 10, slightly higher. 1850, these are kind of inconvenient on the axis I put down, but I'll think of right around here is 1850. Temperature was 8.3 degrees. Finally, almost the last one, 2,100 meters. This is way above our altitude. We're at 7.1 degrees. So that's my best guess at that relative location. It's harder to place it precisely further right till we go. And 2,400, we're at 4.9 degrees. So about here. So here's our data. It's not perfectly plotted, but even if we did plot it perfectly using technology, not all these points are going to fall in an exact line. But you know, there is a pretty remarkable pattern, though. They're close to it. Real data has variations, so we're expecting things to be a little bit off. Sometimes it's really off. Sometimes your dots vary in this big way. So we want to kind of quantify that, say to the degree, the strength that the relationship is apparent. But so far, this looks like a pretty striking relationship. As the meters increases above sea level, the altitude is dropping. Well, that's our first one doing this by hand. Any questions at all getting this down? Okay, tough part about all these problems you probably have noticed so far in this class is to say something about it. It says comment on the scatter plot using the context. And obvious things that we would talk about would be if there's an outlier. An outlier would be an observation that might look something like this. And that would be really weird, right? If you're somewhere close to 2,400 meters above and the temperature is way up here, that would be remarkable. We'd probably think someone made a mistake. Maybe they moved a decimal point when they recorded the data. Maybe the instrument wasn't calibrated right. Maybe some wild animal laid down next to the device that's recording the temperature. Who knows what happened? But that would be an interesting point. We have nothing like that. These dots fall pretty precisely on a straight line. So because it looks like a line, and because the values are going down, we might start by saying that the relationship between the altitude, here when we're mentioning the context, we definitely have to mention both variables at some point. And so now we're mentioning altitude above sea level. the relationship between altitude and temperature. So we're definitely hitting the context if we bring in those two words there. And now we just have to say something. There's a lot of things you can say about this. Again, there's an outlier, then that's a dead giveaway. Mention it, and that would fulfill the requirements of this problem, unless it said to mention two things or more. But getting started thinking about this, you might say the relationship is linear because these points are very close to falling on a straight line. Let's start off by saying that is linear. Next thing you might want to mention is, well, what kind of linear? The points could be going up, like on our first example on these notes, but these points are going down. They're decreasing in temperature. So we'll say it is linear with a negative direction. Saying it has a negative direction is just the same thing as saying the values are going down. You can say this in a lot of ways. You might say it's linear with a negative slope if you're more mathematically minded and you like to think in terms of slope and intercepts. But I think this would make more sense just saying as a general description of the data that anyone who, whether they've taken statistics or not, would understand. The points are basically just going down. And there's maybe one more thing you'd want to say at the same time. The fact that these points don't scatter much across an imaginary line if you drew it, all the points would be very close to that line. So we might say the strength, let's say, and the strength of this relationship is very strong. And that's all we would have to say for just a quick rundown for these kind of data. So getting started, we do have to mention altitude and temperature, and then just mention the main features that you see in the data. Well, we did it, folks. This is our first rundown describing data whenever we're dealing with two quantitative variables. Any questions or comments getting through this, or any other things you'd want to mention? Okay, just to tie together what we've been doing in the past, we really aren't doing anything too different from section 2.3, for example, or section 2.2. And these sections, way back in section 2.3, it was just one quantitative variable. And the way we described how the variable is expressed is through the shape. We mentioned things like unimodal versus bimodal, symmetry versus skew, and we mentioned the outliers. If it's two quantitative variables, we're just mentioning if the data is linear or not, if the direction is negative or positive, and how strong the relationship is, how tightly the points scatter across that imaginary line if we drew it. So the imaginary line in this problem would look like this. We'll put it in orange to say it's an optional part of the work. The line that seems to get close to all these points, hand drawn, would be about like this. I'm going to cheat a little and draw it, move it around like that. This is what chapter 7 is all about, putting the line down. And when it was one quantitative variable, this is what chapter 5 was all about. Just putting a curve to that data, that was the normal distribution. So even though these problems look really, really different, we're trying to do the same kind of thing. This is going to be modeling all values, the population now, based off scientific measurements like this. Well, our goal is just to get more practice doing this kind of thing, describing these relationships, which is just what we were doing over here, getting more practice describing quantitative variable, describing the histograms. In that goal, we have a big definition. There's a lot of things that we'd like to mention whenever we're looking at a scatter plot. The direction, whether it's a positive association or a positive direction, means the points are going up as one variable increases, so is the other. Negative association or a negative direction means as the points will go down as one variable moves from the left to the right. So this one looks like a negative direction. This one looks like a positive direction. So the scatter plot, we want to mention the direction, also the form the points take. The form could be straight, or you could say linear, like we said in the last problem, or there could be other patterns that emerge. This one looks a little bit odd, for example, and so does this one. So the first two panels we see on these notes are pretty odd exceptions that we're taking a look into. But the next ones look like they're pretty straight or linear relationships. We want to mention the strength of the relationship, whether it's strong or not. And this is where you have to do this in a qualitative sense. The good news is we're going to put a formula down for that. It'll be called the correlation coefficient later on these notes. And we'll have a rule of thumb to say, when is this relationship strong? When is it weak? Or no relationship? And we also want to mention any outliers anytime we see them. So here's the 4 bullet points. Let me compact them just a little bit so we can see the displays below. We just want to practice doing those kind of categorizations for these data below. So there's no context whatsoever for any of these data. All we know is that there's some explanatory variable in the horizontal direction, some explanatory variable in the y direction, the vertical sense. We want to describe the direction, form, and strength for every one of these plots. Let's go column-wise because this is the weirdest one, it turns out, the upper right cell. First, on this one, as I go left to right, reading the scale, the points tend to increase. So we can say that this has a positive association. Next thing we want to determine is this relationship linear or is it a straight line relationship? Looking at these data, what would you all say? Does this look linear or something else? Let's really look in on that. It's one of those things where we just have to get some experience doing this because if I draw a straight line, it might not look like it's doing too bad of a job unless you really focus on what this line is doing. Right around here in this range, whatever those values happen to be, in this range, most of the dots are above the line. In this next range, from around here to here, most of the dots are below the line with very little exceptions. And then when you're on the upper range, from here, most of the dots are above the line with very minimal exceptions. A good linear relationship will never have that kind of feature where there's some kind of pattern to how the lines are above and below. And it doesn't matter where I put this line. If I drag it down, I'm just making it even more exaggerated. If I drag it up, it's more exaggerated in a different way. There seems to be no compromise. What we would really like to do is bend this line. Would you all agree that the better way to try to get a line or a curve to these data is to give it some curvature and do something like that? Would you say that's the better model versus the straight line? Awesome. Some folks agree. And the idea is no matter where I'm at on this line, the dots are above and below pretty much randomly. Here's a bit of an exception, right? Maybe the curve could do a better job. Here's a bit of exception as well. So we can imagine if we were to refine this curve, I shouldn't call it a line any longer. It's no longer straight, but if I go like this, maybe it shoot up a little bit faster in this region. This line seems to be doing the better job of describing the relationship between the horizontal variable and the vertical variable. That means the form of these data is not linear. So let's just say it here, non-linear form. And now we have to do the kind of uncomfortable task of deciding how strong is the relationship. Well, I would say that this is a pretty strong relationship, but it really just depends on your eye and how you're interpreting it. We need a good statistic that's going to tell us without any shadow of doubt, without any say, debates and interpretation how strong the relationship is. But first, we're doing it qualitatively, so this is somewhat subjective. I would say for the strength of this relationship, this is between moderate and strong association. So that's our data on this one. It's a positive association because the points are going up, nonlinear because a straight line does a terrible job modeling the data, and there is some scatter around this line. It's not kind of like in the last problem where the points are very, very near by the line, no matter where you're at. This would be an extremely strong relationship, for example. So we called it moderate as in average strength, to strong. I gave it a whole range on that, since if you did say strong on this one, that would kind of qualify for these data as well. But that's one down. Our job is to just see what else can happen on these notes. If there was an outlier, we would have mentioned it, but we didn't see one here. All the data seems to follow this growth pattern where the growth rate increases the faster we move to the right. An outlier would look something like, say, this, or maybe a point way down here, something that's just way away from the main grouping of the data, not fitting the pattern. Even something like this point is unusual, because in this range, all the points seem to be way above. Sure, it's close to the main grouping of the data, but when you think in terms of just the vertical direction alone, that's pretty far away all of a sudden. So that would be an unusual point as well. But we didn't see any bona fide outliers, so that's where this one would end here. Now we just want to try it all over again, but any questions or comments at all looking in the first grouping? Okay, we'll look into problems with context, but for the moment, here's the next grouping of data. What would you call this one? Positive or negative association as you see it? Yeah, absolutely. This one would be negative because as we go left to right, we're always reading the graph in that direction. The points are falling. So kind of like the example that we just looked into for the temperatures and altitudes, that one was a negative association. You know, it helps to put a line down to see it as well. So let's draw that in. So this has a negative association. I'm not going to fit that word there. This time when I drew the straight line through these data, no matter where I'm at on the line, points are kind of randomly above and below in all regions. Maybe a little bit off on here with the 3 points below and just 2 above, but that's no big deal. It kind of split them up pretty well. If you can draw a line that seems to get between all the points in this kind of way, this is an absolute linear relationship, or you could just say a straight relationship. The book is more often to say linear, especially in the MyLab statistics. So say here, this is a linear form, using the word form just because of that part right there. You could just say linear for full points on this one. And looking at the spread of these points across the line, it's a little bit more tightly packed. All the points are more near versus the last example, the one that we looked at above. So I would say for this one, very strong association. As one variable changes, the other one changes in a very strong way as well. So far, these are kind of the normal plots. Let me kind of move these around just for more space. Does not move in an easy way. That should have done it. Oh, I forgot I drew in a point. That's kind of a dead giveaway that a point's been drawn in if the graphics don't move in a nice way. So I drew it again over here as well. Let me just make sure it looks the same. Sort of. Okay, it was way over here. So let's look into this one. This is the weirdest one ever. This might be something you get if you're looking into, say, stock market data. The horizontal axis could be time, maybe days. The vertical axis could be the amount that the stock is trading for at the close of that day. And sometimes there's just no apparent patterns. Sometimes things are going up and down just completely randomly. This one is really pretty bizarre. Would you say positive or negative association to this? Or does it even make sense? Are the points, in other words, moving up or down, or none of the above?
Oh,
Kind of in a way, yeah. From here, it jumps up. Then from here, it goes down. The next one down a little, then jumps up again. It looks like it's just all over the place. If you were to put a line to these data, the line that would do the best job would look like this. Just a flat horizontal line, no slope at all. In fact, the height of this horizontal line would be the average of the second variable on all these data points. What I mean by that is if we look into some actual data, if you take the average of all these temperatures, you would get a line that looks about like this. That horizontal line doesn't describe these data. It does a terrible job. This is the height of what the sample mean y bar would be. But on the problem down below, the sample mean y bar, if you draw it in as a horizontal line right at that height, that looks like the best way to describe the data. Whenever this happens, pretty much all of this stuff is off the table, unless there's one point way out here for an outlier. This is the one and only graph where this would be no relationship. Let me try to fit that in as one word. Between X and Y. So this would be the X-axis. Going up this way would be the Y-axis. That's getting kind of too busy, so let's take that off. Whenever it looks like just white noise, just scattering of points like this with nothing as a pattern that you can see whatsoever, this is the no relationship picture. And that could absolutely happen. Sometimes our variables have nothing to do with one another. If that's the case, you see this kind of pattern. One variable is not influencing the other in any meaningful way. This is the total opposite end. There's an extremely strong relationship. A change in one variable causes a striking change in the other variable. But if this was a lie, if we're on some weird universe where this didn't actually happen, then we would see this instead if environmental lapse was a false concept. So watch out for this one, especially in MyLab statistics. None of these concepts have any meaning any longer whenever you have the no relationship. So we just end our description right at that step. Well, any questions at all, folks, getting through that one? Okay, so really the last row here, these two, these are the normal things that we would like to see. In our textbook, the only relationships we're really going to analyze is the linear ones. The more statistics you take, there's an entire course on dealing with these kind of models called regression analysis, kind of a crazy word. And so you can model these data, but it goes beyond the scope of what our book covers. So on the very last one, let me fix my colors here. We're looking into these data, and we try to draw a straight line. We might draw a line that goes about like this. It's not perfect. We can move it around to try to make it look a little bit better. But no matter where we put the line, no matter how we maneuver with the slope on that, this point is really the odd one out. So maybe let's just start this one by saying there is one outlier. That point way out here. So there is an outlier. Outliers always mean the same thing. It's a point that just doesn't feel like it fits the pattern of the data that we see. Not fitting the pattern could sometimes mean something like this. You have right skewed data. None of these were the problems in the right skewed data because it fits the picture of data essentially being modeled by this kind of curve. But that one was weird because it was just so far away from the main grouping of data. But now we're looking at data in 2 dimensions. This one's far away, not because it's different from all the x values. As an x value, it's typical. it falls where all the other x values would fall. Imagine gravity affecting this plot and it turns into just an ordinary dot plot, like we looked into section 2.2. In section 2.2, that dot plot looks like this. So if we took away the y variable and gravity affects all these points, they just fall down in this kind of pattern. And then this point is not an outlier any longer. It's only when we look into it in 2 dimensions, when the second variable is on the paper, that it starts to stand out a little bit more and becomes an outlier. Now it doesn't fit the pattern of this relationship here. Well, aside from that, we can also say the line is going up from left to right. So this is a positive relationship or positive. You could say relationship, that'd be synonymous with association. So let's say it here. There's a positive relationship. We can say also that this is, even with an outlier, it does still have the straight line relationship. The line we're going to build with our calculator will be influenced by this, but it'll still be a straight line. So it's a linear form. Then last thing, we just want to describe the strength of this relationship. Really not too different from this one. Maybe slightly different spread, but we're doing this by eye, so I'd probably still call it the same, a very strong relationship or association. Very strong. Let's go with the word relationship just to convey it's synonymous here. So these are the 4 different graphs that can happen in this course. The nonlinear form can take on lots of different things. It can maybe be a wave that we see. Here we just saw it turning up in this way. But anything that doesn't fit this linear form, we just call nonlinear altogether. So our goal is to study this, see how to do these kind of descriptions again, but now with context. That's what makes it all a little bit more interesting. Any questions at the moment with what we've got so far? Okay, for the next problem, we'll be using the TI-84 because our goal in the next problem is to determine which one's explanatory, which one's the response, and then construct a time series plot. We're going to do it differently this time. Sure, we could do it by hand, and you could do the same in the MyLab Statistics homework, do them all by hand. But if you have access to technology, we might as well practice actually using the technology. So on MyLab Statistics, they'll give you the option to create a scatter plot. But what I would encourage you to do is take the data, put it into your calculator, construct the scatter plot yourself, and you'll see which options match. It turns out they're all multiple choice questions. This is how they're going to be done as a quiz problem and an exam problem as well. This saves us a lot of time as well because it can be tedious to plot all of our data, especially if there's loads of data values. First things first, we have to decide based on the context, which is explanatory. So this says the report credit card and debit card fraud statistics included the data in the accompanying table on the amount of money lost for fraud for each of the years from 2001 to 2012. So this is money lost. It says specifically to online fraud in those years, and this is in billions of dollars. So this is impressive. I thought it was millions for just a moment. So for example, 2008 was an interesting year, $4,000 billion of fraud for online. Pretty impressive, that amount there. Seems to be a pattern to these data. It's going up, but there's a maximum of 4 billion in 2008. And it seems to kind of have leveled off just looking at these data. Well, looking at this, which one would you say is the explanatory variable? Is it year or money lost? The year. Yeah, good call. The year is going to explain how the amount of money lost in billions of dollars is changed. But we also mentioned something. When you format data like this, we're not going to try to do it in a weird, silly way. We mentioned last class, the thing that comes first is the explanatory variable, because that's the way any sensible person would have formatted this kind of table. The only reason you would switch this up and make it confusing is maybe it's a MyLab statistics problem. So watch out for those. That could happen there. We're thinking of year as being explanatory because it seems to be the impact on how the money is changing from fraud from year to year. It's hard to imagine how this is explaining the year going in the opposite direction. So because it's the explanatory variable, year, it means it's going to be the variable x, the one we would plot on the horizontal axis. Likewise, this is the response variable. I'll just call this money lost. So this will be the variable y. Now we want to plug this into the calculator. And again, this could potentially save us like 45 minutes on the homework set because plotting these things are tedious. And if we plot them slightly off, then we could lose the question by selecting the wrong answer. Plotting these things on the calculator is a little bit tedious. Here's the sequence of steps you'd want to take just as a one-time setup. I also post this on the document here, the TI-84 scatter plot instructions. So this is primarily for the homework. On an exam situation, you're not going to be asked to do this on a calculator. I'll have the scatter plot already pre-printed. It'll be our job to just interpret it. So here's the instructions that I copied down from another website. I copied it so that we didn't have to experience the ads on that website. It says, hang on, this is the correlation coefficient setup. My windows are a little bit mixed up. Go to the scatter plot instructions, and these are the instructions that they're going to walk us through. Part of this is just a one-time setup that we don't have to do every time. And if you bought a used calculator, then some of these things we do have to change around. If it's a brand new calculator, it might be set up correctly already. But here's what we want to do to start this off. Hit the second button. You should see the up arrow right here flashing, and immediately click on this y equals for stat plot. Let me make this calculator a little bit bigger so we can see all those little things there. So everyone should see this window at the moment. So it says everything here is off. Actually, this is a setup I have to do because this calculator resets every time I turn it on, I think. It needs to have off down the line here, but the top one should be turned on. So with option 1 already highlighted, just hit enter right away. You should now be on this page. What we want to do is turn this plot to on. So we just hit enter again to toggle that. So your screen should look like this. The thing that's flashing should be highlighted as well. Also, if you have anything else, like maybe, hang on, maybe if your calculator is used, it could look something like this. This is not going to give us the display we want if this one's highlighted. The scatter plot is going to be the very first one. So your calculator should look like this under type. If it's not, hit down arrow, hit enter. And if I hit the up arrow again, so on is flashing, the calculator should look just like this. Critically, L1 and L2 should be those things on these two spots right here. If for some wild reason this looks like this, maybe someone had data they didn't want to erase and you have L3 there, our plot is not going to look right unless we put the information in a really weird way now. So to bring this back, go down to where it's flashing right here, hit second, and the number 1 button to put in, hang on, L1 was the hope. Let me try again. Uh-oh. Second, L1. It worked this time, just not the last time. I think I had something like alpha selected for the letter Y instead. Okay, so if I'm back on the on flashing, your calculator should look just like this. Off shouldn't be highlighted. This should be the one thing that's highlighted here, and it should look like L1, L2. Is that what about everyone has so far? Okay, so that's what step one is all about. They said a lot in one step. Now, the next thing that, again, if this is a brand new calculator, probably there's nothing there. But if someone's been using your calculator, you have to also do the step two. So you should be able to hit the y equals button right on this page. And it brings up all of this stuff. There should be nothing here. It should all be vacant. So if you had something like x squared minus 3x plus 5, then someone was just doing something interesting in the calculator. They're plotting this function, but it's going to mess up our plot. So what you'd want to do is just hit delete a bunch of times, or maybe hit the clear button so that there's nothing there. I hit up arrow and down arrow just to reset the vertical width on that. So this is what you should see on this screen, in other words. On plot one, there should be nothing at all. So that's what this is saying. Clear out everything so your screen is blank. Is that what about everyone is seeing on this page here? Okay, after all that, I would then, at this point, never mess with these functions again. Just leave them exactly as they are. We'll never have a cause to go back to second stat plot again for the rest of this course. Everything's set up the way we want it to be. At this stage, it's going to feel kind of like what we did way back in the day when we were in, say, chapter 2, doing summary statistics. Let me reset the size of this thing. So very next thing we want to do is just import all this data. So go hit the stat key, go to option 1, edit, and now we're putting in data. Clear out anything you might have, up arrow and then clear right here, deletes the entire column. And here's the next thing you probably want to convey on the notes as well. When we say the explanatory variable, we're referring to, in our calculator, L1. You can change the roles, but that could be really confusing. My advice is keep that L1, and you're always going to be plotting in the way the data table has been formatted. So L1 should always be your explanatory variable. L2 should always be your response variable. So now we're just using two columns. So again, not too different from what we did in chapter 4. Now we just do the dutiful task of being really, really careful plotting in all these data values. I'll just go column-wise, put in the entirety of column 1, and then put in the entirety of column 2. So I'll get quiet while we're typing these in. One of the things I should have done first is also count the sample size. There's n equals 12 rows, and that just helps me make sure I've got the right amount of data when I go into that column. Then right arrow and do it again for L2. It's slightly tedious. Okay, I think I've got all the data inside there. want to put on the notes just some steps down here. These are the steps you'd repeat each time that you do a new scatter plot. Step 1, hit the stat key. And then I forgot what after. Hit enter on enter, hit enter on edit. Then import the data. And your calculator should look about like what we have here, where we're not showing all the rows, but about like that. So the very first step is to make that happen in the calculator. Then the next step is all about that button. So let's write this in. So this button has everything we need. Hit this and option 9. So for step 2, let's write this in just so we have a paper trail in the notes. Step 2, we're not writing in those other steps with hitting second y equals because it's a one-time setup, thankfully. So step 2, hit zoom, then hit enter on option 9. Let me see if my memory serves me right on that. Hit the zoom key. That didn't work at all. Let me back out of here. Let me go second quit. Worked that time. Let me go second quit. Let me try this all again from the start. Stat, enter, so my data is in there. Then hit the zoom key, and it worked that time. Weird. Well, it's an emulated calculator. Let's just say that was a weird glitch this time. Does everyone see this so far after hitting the zoom key? Okay, if you scroll down, there's lots of things on here. Option 9 is what we want, zoom stat. It kind of makes sense, right? It tells us it's going to give us a zoom of our data on an XY display showing a nice scatter plot, and zooming in and out the right amount to show the min and max for both variables. So that's where you should be hitting right there. Hit enter on that. And there's our data. It's kind of a rough scatter plot, but if you're doing this as a My Statistics homework problem, it probably saved you some time. Now you can take a look into the multiple choice problems there, see which one matches the most. And that's going to be the experience in the homework set for this section. So let's just call this step 3. There's not much to do here. Let's just call this success because we did it. And our data looks like this finally. Well, anyone getting anything slightly different or weird looking, or does it all look about like this for you as well? Awesome. If I typed in a number, then some of these points could be in a different place. If I missed a decimal, some of them might have went way up or way down. And even though we're doing this primarily for a homework problem, everything we did here from the start, where you went to hit the stat, the enter key to put in the data, this is really important because later on, we're going to calculate this thing. And this is a beast of a computation. But putting in the data just like we did, even if we don't graph the data, we'll be able to calculate that thing right there, the correlation coefficient, with the data imported in that way. So we'll be reusing the steps again in problems like this one down below, even though we're not necessarily required to get a scatter plot to get that coefficient. But finally, we've got it, folks. We might want to add some context to this, so let me get a quick screenshot here so we can remind ourselves of what it was. Scatter plot is right there above. On the horizontal axis, this was year. It started in 2001, ending in 2012, it said. Then on the vertical axis, this was our explanatory variable. Going this way, this was money lost. And this plot is kind of unsatisfactory because it doesn't give us too much if we're just staring at this. But another thing you can do on this is, let me go back to zoom. You can just press 9 to get here. If you use the left and right arrow, it gives you some coordinates for where the cursor is. That's extremely tedious if there's somewhere you want to go, right? But you can also hit this key. This key right here is the trace key. And once you click on the trace key just once, your cursor centers on the actual data values. So you can move left to right to see the data replicated again throughout here to see what those values actually were. For our plot, we can see that it minimizes for 1.7 billion, and the maximum value was at 4.0 billion. So there's our scattered plot. Took a lot of work to get to that point. We've done the part where we've constructed the scatter plot using the calculator. And now we want to do this part, describing the trend over time using the context. Let's see if we can possibly fit this in here on one page. Yeah, that might work out. So we want to use the context. This is the year. This is money lost in billions of dollars to fraud. First thing we want to decide is, if we're describing the trend over time, we're mentioning the form, we're mentioning the direction, and we're mentioning the strength, and as well as if there are any outliers that we see. So a lot of things at once. Let's first start with, how about the direction? Would you say that this is in the positive direction or in the negative direction by what we see? Yeah, good call. The data points are moving upwards as the years increase. So we can say that the association between year, actually, sorry, I should probably not use that color coding. It's already been used up. I'll just go with black. The association between the year and money lost in billions to fraud. It was specifically online fraud, but again, you don't have to mention every bit of the context. We'll let that be something that's carried along the line in the full context. So to fraud is positive. So this was part of the context, the fact that we're dealing with year as a quantitative variable. And this is the other part of the context. The other quantitative variable was money in billions of dollars. And hang on, let me look at that scale. Oh, I think I hit enter a bunch of times and moved that around a little bit. That was supposed to be way up here at, it's not coming off now. This is supposed to be way at 4 billion up here. So it's in the positive direction. Now, tricky question for you all is, would you call this one linear? Sorry, say again? I would say linear might be a good option on this one. Let's take a look into it. If we draw a straight line, it would look about like this. It's kind of a judgment call because something happens out here, which is a little bit weird. When we're on this region between these years, the points are randomly above and below. We can kind of target it slightly better. But then out here, there's a smattering of points that just seem a little bit different. It's only 4 points. So honestly, it's pretty borderline. But I would argue these might be more nonlinear data. Let's take a look. If we instead let our line bend a little bit, the line could look like this instead, starting off linear, but then kind of leveling off like this. In this region, the dots are above and below, kind of a little bit more spread out, 3 above, 3 below, but we had to bend the line to make that happen. Let me try to make it slightly more straight in this region, and then bend it out in this region. Would you agree that this is slightly a better model if we bend the line? Awesome. Again, I would say this is a tough exam question. It would be kind of borderline. I would probably accept linear on this because we haven't studied a lot of these graphs. But I think the actual official answer to this one would be, after a lot of practice, this one is probably better classified as nonlinear. These grouping of points have so much leverage that the better way to model is a curved relationship like this. So the next thing we can say is, forgot what color this was. We're trying to compare these. I'll go with, dang, we already used up green. So we'll just write this out. The form is nonlinear since money lost begins to level off. After a certain year, we can look into the data. Maybe that was about halfway through, right around 2006. Something happened. Maybe the FBI just got way more sophisticated, who knows? But this begins to level off around 2006. And how about for outliers? Anyone see any outliers, or would you say it's all about the same with these points?
I originally would want to argue with you with the 2006 comment, but
What year would you place on instead of 2006 on it?
I would word it since the money lost, since the money begins to level off after 2008.
Yeah,
The
2008.
trend goes all the way up till 2008.
Yeah, that's the maximum
The
there.
change hasn't.
I see what you're saying. Right around here, this is looking pretty good. But then it's through here, it's leveling off. Yeah, I see what you're saying. Let's add that into the notes. I think that's a great way to look at it. So if we were drawing just one complete line, it might go like this, but if we're tempted to get through all the points, it's leveling off like that. But the change was really around 2008. Yeah, I think I would agree with you because that models it pretty well until that happens. So let's go and say begins to level off after 2008. That looked like a good way to write it in. Again, it's being kind of finicky because there's lots of ways to interpret these. It just seems like the points are randomly above and below. That's 3 above this time, and looks like 2 below if you drew it like this. There's even more weird things going on with this data. If you were to attempt to say what the strength is, say weak, no relationship, so this is no strength at all, to moderately strong to very strong, it's a challenge on these data, and it's a different kind of challenge than we've seen before. Because right around here, you might say that's a very strong relationship, right? The points are pretty close to the line or the curve at that point. But once you're beyond, say, after 2008, or even saying from 2006, as the line is drawn, to 2012, from here, as we ended up drawing this line, it started to spread out a whole bunch. We're not going to try to draw a line that ever goes like this, for example. This would be considered cheating. So we're not trying to do this at all. We're still trying to draw a line that goes about like this. One line that attempts to get close to all the points, but not in any kind of zigzag way. So there's a weird thing happening with the string.
You say that then?
Yeah, absolutely.
You say that the first 5 years of the data, there seems to be a strong relationship, and after that, the relationship comes undone.
Yeah, absolutely. That's a great way to say it. So this would be kind of a worst case data for our course. Modeling these data, even if you have nonlinear methods, is still a challenge because the variability changes from year to year. Let's say it the way you said it. In the first 5 years, the strength of the relationship is I would say even very strong on that. That's a pretty tight grouping. In the first 5 years, the strength is very strong. Then it becomes, how would we say this? Well, we might say moderate to weak maybe for these. We need a good number that's going to put that down. So we're not just eyeballing it and guessing every single time. We're getting there. That's going to be the correlation coefficient. But we could say becomes moderate to weak, just to put something down on paper. If you said weak, well, it's not the weakest relationship. They could be more spread out with still a relationship going on. It's somewhere in the middle of those values. It'd be nice to just state a number, and that's what we're trying to get to. Again, these are some really weird data. Linear seems to do good except for that grouping of data. And then the spread of the data, the variability changes as well. And something seems to happen in 2008. After 2008, maybe people who are doing sophisticated online fraud and the FBI, other agencies were playing kind of like a cat and mouse game. And that's why some years it was major, other years it was very minor, then jumping back up to even more fraud. It was as if new tools are coming out and new different kinds of frauds were being invented. But who knows what the real story is with this data? All we know is it's got a pretty weird look just based off the scatter plot alone. Well, any questions at all, folks? Getting through this one? Okay, again, our goal is to put a number to this. That number is going to be this thing, Peirce's sample correlation coefficient. It's a mouthful. It says a lot. What we want to do is look into scatter plots again to get a feel for what is this new statistic even trying to say. There's two major challenges for us. We want to get a view of what the statistic is trying to measure, what the rough value would be if we saw data like this versus data like that. But we also want to try to understand the formula. It's a crazy formula, but you know there's a tie-in. If you look at this part right here, we did this kind of stuff before. This is all the way back in chapter 5 on, let's see if I remember where that was. I think it was 5.1. Already feels like that was a while ago. So if you look at this one, we gave it a subscript y because now there's two quantitative variables. So this is the z-score for the y data. And it's in the same kind of formula that we used here. We put in y bar. S has a tag y, so it's the standard deviation for the y data. So we're using standardized values. We standardize the y values, we standardize the x values, we divide by n minus 1, and that's the correlation coefficient. So we really have three jobs now. We want to understand how the correlation coefficient ties in with these kind of graphs, whether it's positive, negative. We want to see what this formula is trying to tell us. Then we're going to calculate it in our calculator. First steps are just going stat, importing the data. We have another one-time setup so we can get the correlation coefficient. And then the final thing is we'll use this rule of thumb. When we say something has weak or no relationship, that means the correlation coefficient is going to be 0. And we saw data that looked just like this. Way over here, sorry for the random scrolling, this would have a correlation coefficient. R is 0. There is no relationship at all whatsoever with these values. If the relationship becomes very strong, but positive, we're on this end. So that's data values that look like this. Somewhere on the moderate is going to be something that looks kind of like this. Still has a direction, but there's some variation on those data points. And something that looks like a -1, that would be this problem right here. Right here. There we go. This is approximately -1 as a correlation coefficient. It's almost perfectly on the line. So this is remarkably tight grouping for data. Again, it is made up data, but if we ran that experiment, it'd be pretty similar likely, since that effect has a very precise correlation. So those are the things we're going to look into when we come back next class. We'll try to understand what the formula is saying because it ties in with z-scores from back before. We use the graphs to get a qualitative view of correlation coefficient. And then we'll just hammer it out with the calculator. We'll see how to just crank this out so we're not spending what would take probably 45 minutes to calculate R for just these data right here. It's a huge computation. But that's what we'll look into next class. This is 5 minutes to try to get into those topics, so we'll end the class a little bit early today instead of jumping into it. Any questions at all before we call it a night?
So the calculator will do that,
Absolutely.
that formula.
Yeah. The way to make it happen is you have to go to second, and then you hit this catalog button for the one-time setup. So if you'd like to see it done right now, we still have a few minutes.
Sure.
This catalog button right here, let me show it just one more time. Hit second, and then the number 0 to bring up the catalog. That's kind of a weird statement, but this is now every single function in your calculator. You're scrolling down to the D's for diagnostic. So just hold down the down arrow until you get to that function right there. The arrow pointing on diagnostic on, hit enter, hit enter again. And I love what this calculator does. Something happened. All it tells you is done. And then you've got it right there. Now, next thing you do, let me see if I remember this. This is the part that's a little bit foggy for me. Stat calc 8. Okay, let's do that. Hit the stat key, go to calculate, go down to option 8. This is the linear regression line, ax plus b. Hit enter there. You should have L1 and L2. Frequency list should be vacant. And just hit enter through all of these. And it gives you a huge smattering of data. But let's compare it to what this was. R is the value that we want to calculate. It's 0.77, which tells us, well, aside from the nonlinearity and the weak grouping here, this was a strong and positive linear relationship. By the rule of thumb, it was, well, I guess it would be moderate strength. I guess the last points bumped it off of strong. So it got pretty close to the 0.8, between moderate and strong, pretty close. It is just a rule of thumb. And that's how these data here, you can use a correlation coefficient on. However, keep in mind, one other big takeaway is this part right here. The correlation coefficient R only measures the strength of a linear relationship. We said part of it is nonlinear once we move off to this end. So even though we could put an R value to this, it's probably not the best R value we should be using. We should be bumping up the regression to something nonlinear and get a more accurate value in here. But that's just a first look at doing that computation there. Other questions about that so far? Okay, we'll practice this some more when we come back on Thursday. I think we have enough time to finish the notes. There's just one more problem to go in full and a couple more concepts that we'll look into. So we may start chapter 7 as well next time, but really it's just doing the same kind of stuff. Chapter 7 is more about that actual line, y equals ax plus b. But have a great night, folks. We'll go back right here to this spot when we come back on Thursday.
Where did we go after we did catalog?
Oh, so after catalog, hit the stat key here. Then go off to calculate as if you're in chapter 2. Yeah, that's the part I forgot about as well. Then, actual option 4 works just the same way, except our book has it written as a plus bx. That's why we're using option 8.
That we went over the calc. I was just
Yeah. Yeah, that's what I was feeling too. That's why I usually put down a paper trail for things I haven't used in a while.
Thank you.
Yeah, you betcha.
I don't do good with cliffhangers, man.
Yeah. I mean, that's also, that means your mind is just craving to fill in that information, makes learning a little easier.
Yeah.